It begins in darkness. Beneath a crust of fractured ice on a distant moon orbiting the giant Jupiter lies something extraordinary. Europa, a frozen world, smooth, silent, deceptive. And beneath its surface, a secret ocean, vast and deep, possibly teeming with alien life. This is no ordinary ice ball. Europa has more water than Earth, trapped beneath a shifting, cracking, moving shell of ice. Tidal forces from Jupiter stretch and squeeze its interior, creating heat. Enough heat to keep that ocean liquid for billions of years. But here's what truly changes the game. Radiation from Jupiter splits surface ice into hydrogen and oxygen. Minerals from a rocky core may seep upward into the sea. Volcanic vents at the seafloor could release heat, methane, and other life-supporting molecules. We're not just talking about conditions that might support life. We're talking about everything we know that does support life. Right here, packed into a hidden ocean no sunlight ever reaches. And it doesn't stop there. On Io, volcanic hellscapes explode with sulfur plumes taller than Mount Everest. Enceladus fires jets of salt water and organic molecules into space from beneath its icy crust. And Titan, Saturn's haze-shrouded giant, holds rivers and lakes of liquid methane. These worlds challenge everything we thought we knew. They tell us that life might not need Earth-like conditions. It might thrive in places we once thought impossible. Europa is at the heart of that revelation. And if life exists there, in the pitch black under crushing ice, it won't be surface-dwelling plants or mammals. It will be strange, alien, possibly complex, and very real. What NASA's Voyager, Galileo, and Cassini missions uncovered already changed history. But what comes next could change humanity forever. Because this is no longer the question of if we are alone. The question now is, how soon? Europa is a top candidate for finding alien life inside the solar system. This is because of the plenty of water, probably in liquid form, protected from the extremes of space by a sizable layer of ice. Reflecting the gravitational influences of Europa's big parent planet, Jupiter, and its larger neighboring moons, Io, Ganymede, and Callisto. The ice shows agitation, constant breaking and movement in rafts and slabs. Gravitational flexing marks only the beginning of the story. Jupiter's intense radiation is upsetting a delicate environment by disassociating water molecules at the surface into hydrogen and oxygen atoms. A slight distortion of Jupiter's electromagnetic field at Europa suggests either a metallic core, a saline ocean under the ice, or both, rotating asynchronously relative to the planetoid's surface. This can point to strong worldwide water currents, an internal heating source derived from radioactive decay in the core, or both. Deep ocean Europa could have thermal vents, hydrogen sulfide emissions, and organic molecules like methane coming from the mantle. These can be the fundamental building blocks of polymeric chemistry and provide other energy sources, enabling life requirements. Originally named Europa by Simon Marius, Galileo first saw Jupiter's moon. It seemed like a tiny dot in the heavens next to its planet. Only following the Voyager 2 flyby in July 1979, close-up images of Europa revealed their rather unusual qualities. Slightly smaller than the moon, a satellite displayed a very different feature. The solar system's most luminous and smooth surface, almost free of craters yet dotted with elongated lines and arcs, evocative of a broken eggshell. This smooth surface and lack of craters are essential since they imply a relatively young surface, indicating continuous geological activity and a subsurface ocean. These are significant determinants in the search for extraterrestrial life. We are aware of the probable composition of this planet's interior. We can determine its general density using our knowledge of its volume and the technique of calculating its mass, depending on the gravitational attraction that changes the path of passing spacecraft. Knowing the density of water, we can verify that the total mass of water cannot be derived from water ice by itself, indicating the presence of a solid mineral core. A reliable estimate of the internal size is obtained by considering a stony silicate mantle around an iron-nickel core, and knowing the densities of silicates and metals such as iron and nickel. The surface is solid ice based on the biographic signature, smooth surface and high albedo. The surface is solid yet dynamic, as the constantly shifting ice plates glide, collide, and reorganize in a turbulent configuration. Large fissures running across the planet reveal surface cracks and possible underground explosions. These lines often cross at right angles and resemble soft arcs rather than being always straight. Frozen surface plates glide past one another to produce complex geometric forms that cause significant slip faulting. Sometimes, these formations are filled with rising liquid that freezes into deeper holes over time. Ice plates slink over one another in the chaos zones, like jigsaw puzzle pieces gone wild. Unlike those on nearby Ganymede and Callisto, the noticeably low number of craters points to a surface that has resurfaced either regularly or at least lately. Because of the strong gravitational influences inside Jupiter, Io, and the orbit of Europa, all the above characteristics match the predictions for a frozen water shell subjected to tensile and compressive loads. The likelihood of ice melting under the surface rises with the possibility of continuous compression and expansion, producing heat. An essential clue of a subsurface liquid ocean is the existence of Jupiter-induced anomalies in Europa's strong electromagnetic field. The most straightforward theory for this phenomenon is a mobile, electroconductive substance inside Europa, a dynamic saline liquid ocean. This point of view is strengthened by indirect evidence showing internal rotation exceeds surface rotation. The last note on the surface is that the scattered ice fragments and the large fracture lines, bordered by minerals, imply the existence of a layer of dynamic saline water, which helps the ice plates above to migrate. An oxygen-rich atmosphere is one unique quality possessed by only a small number of solar system celestial objects. Europa's atmosphere is incredibly fragile, comprising only 1/100th of Earth's air and far less density than Mars's. Minimal atmospheric filtration causes radiation to rapidly escape from water at the ice surface into hydrogen and oxygen. Oxygen may progressively enter subterranean interactions with other molecules prone to oxidation by gardening the recently liberated oxygen into the ice, a process whereby the ice is disrupted and reorganized, so burying the oxygen within the ice, and possibly including it into sporadic liquid eruptions above the surface. This gardening process is vital since it helps distribute the oxygen over Europa's surface and into its subsurface ocean, influencing the possibility of life on Europa. Jupiter's 4 main moons have similar beginnings, but their size and spatial configuration vary greatly. We shall clarify how they arrived at their current condition before looking at Europa and Io in the next chapter. One is 99.8% of the Sun's mass gathered at the core of the spinning protostellar disk when it was formed from a sizable cloud of gas and dust some 4.5 billion years ago. All of the planets and their satellites orbiting the Sun account for the remaining 0.2%. 2. Jupiter and its moons are the most massive planetary systems orbiting the Sun since some of the leftover material was incorporated into their buildings. 3. Of the whole, 99.98% went into Jupiter. The other fraction was mainly distributed among the 4 main moons: Io, Europa, Ganymede, and Callisto. 4. The phase consisted of synthesizing silicate and metallic compounds underwater and volatile gas presence. The silicates and metals are made for solid cores. These same elements probably expelled whatever water was condensed initially there. Europa's proximity to Jupiter allowed it to retain enough water to cover its whole surface. Its remoteness from the Sun caused a total surface freeze. Tidal flexing brought on by Jupiter's gravitational forces produces heat and maintains the liquid subsurface ocean. This constantly liquid water makes it difficult to determine the degree of a meteorite strike it gets, since it might either destroy or change the proof of such impacts. Knowing these elements helps one to grasp the possibilities for life on Europa, since the search for extraterrestrial life depends mainly on the existence of a subsurface ocean and continuous geological activity. Comprising Jupiter, Ganymede is the largest satellite in the solar system. Ganymede's water content is commensurate with Europa's. Yet, despite internal heat generation, Europa's surface shows significantly lower temperatures, which causes her eventual resurfacing. The third largest satellite in the solar system is Jupiter's moon, Callisto. Its internally generated heat is far less than that of Ganymede, which results in an old surface with a geologically dormant state. Io, Ganymede, and Europa would oscillate close together due to a resonance period of 1 orbit around Jupiter for every 2 orbits by Io, and 2 orbits around Europa for every Ganymede. This assured Europa would undergo sufficient tidal flexing to prevent heat from seeping into its core. Under its frozen surface, combined with some radiogenic disintegration, especially in its early history, this has created a liquid ocean. Analyzing life's essential components reveals that Europa is the best place for solar system visitors looking for alien life. Europa first has more water than Earth, so the need for a solvent is naturally met, given the many advantages of water as a solvent for biological systems. Multiple possible habitats for life have emerged as evidence of liquid water under the frozen crust, supporting the mantle at the bottom and the boundary at the top, corresponding with life on Earth. If water is the solvent, carbon is most likely the backbone used in polymeric chemistry, which is vital for life. Direct evidence of organic molecules on Europa is lacking. Europa's subaqueous rocky mantle may release organic chemistry precursors such as methane, carbon dioxide, and hydrogen sulfide if the satellite's interior resembles Earth's. We have defined light's advantages as an energy source for biological systems. It sustains most life on Earth and energizes life in Venus's clouds. Jupiter's great distance notwithstanding, the light would have about 1/20th of its intensity on Earth, preserving Europa's surface-dwelling life. The intense radiation and extreme cold on Europa's surface most likely limit any life near the surface to microorganisms living in hypersaline water, inclusions deep within the ice. Enough distance to receive some radiation shielding, but close enough to absorb the meager millimeters, several inches, of weak sunlight that pass through the ice. Photosynthetic microorganisms are the first form of life upon arriving at Europa. A strong ionizing and particle radiation field strikes Europa unhindered, even from the far-off sun. Any surface or near-surface organism capturing these highly charged particles could get a significant energy dosage. Particle radiation's strong and erratic properties make direct use of it an energy source unfeasible. Potentially providing metabolic fuel, collisions with brilliant particles are more likely to generate hydrogen from water. Should water dissociate into hydrogen and oxygen within the ice, a reservoir of hydrogen accumulates and creates a concentration gradient, favoring hydrogen migration into biological compartments. Usable energy could be derived if organisms have evolved the means to seize energy from the diffusion of hydrogen ions across their outer membranes. These creatures would also be microbiological, since they would most likely be covered in minute water inclusions. Still, the oceanic depths under the ice welcome life in more significant forms and diversity. Even the finest estimates for Europa's ice sheet show that it has to be at least several kilometers thick. This makes the underlying liquid ocean completely dark, even if some thermal vents might emit infrared radiation. Should no light find its way to this aquatic environment, other energy sources must support the familiar forms of usable energy for the ecology. Comprising carbon dioxide, methane, and blue chloromethane, hydromethane is readily available as a net energy source. Unidentified chemical processes allow hydrogen and carbon dioxide to leak from the core of the mantle. As Chapter 3 describes, iron is a large atom that quickly gains and releases electrons. This process may also generate energy if hydrogen from the interior reduces iron in the ocean. These reactions cannot operate constantly without the complete execution of the oxidation-reduction cycle. The lowered ions must reoxidize. This could happen at the ocean surface because of unexamined chemical reactions at the seabed or oxygen seeping through the ice covering. Earthly organisms can carry out the described reactions inside their cells using the produced energy as chemical bonds to drive their biological activities. Another potential energy source is the convection of water currents under ice. Although there are no known examples of animals on Earth using kinetic energy to maintain basic metabolic activities, it is admitted that it helps particular biological processes. Some flat, fan-shaped coral-like animals adapt to current flow to gather microscopic food particles. Dynamic fluid waves distort the hair cells in vertebrates' internal ears, converting sound's mechanical energy into neural impulses. Air currents facilitate avian flight. They also help to dissipate heat from animal bodies by evaporative cooling and distribute nutrients via both plant and animal circulatory systems. Water currents may affect cilia by providing tensile energy to molecular structures similar to spring coiling. When spring's tension starts to release, favorable energy becomes available. On the other hand, the bending of hair cells could activate semi-permeable pores, enabling ion movement along their concentration gradients. Chemical energy can be stored more easily with flowing ions for later metabolic release. Evolution's creative character helps us to conceive several mechanisms. A suitable source of biological activity in Europa's large ocean is the potential energy obtained from ionic concentration gradients. Because minerals from the mantle dissolve in water near the ocean level, rather than in water at a higher elevation above the ocean floor, the salt concentration of that water is higher. The seawater near the surface is more diluted than at deeper levels due to the melting ice at the ocean's surface, which has a lower salinity. Living entities can use these gradients by maintaining an internal ionic concentration, or tonicity, that differs from their surroundings. Permitting ions to pass from areas of higher exterior concentration into a live cell's more dilute, hypertonic interior would allow one to extract energy from the ocean floor. On the other hand, organisms close to the ice ceiling could use ions that diffuse outward from their hypertonic interior into the hypertonic surroundings. These events mirror the osmosis process, as if water were moving. Mechanisms within the cell membrane that change the structure of molecules, responsible for chemical storage or start chemical reactions that save energy for future use, could be connected to the spontaneous movement of water into or out of a cell at the surface of the ice sheet or the ocean floor. Although heat may be a significant energy source in Europa's undersea ocean, it does not provide metabolic energy for life on Earth, most likely because of its fast dissipation and relative inefficacy compared to light. Heat could come from two sources: the tidal forces Europa experiences from Jupiter and Io in one direction, offset by the gravitational pull of Ganymede and Callisto in the opposite direction, or the radioactive decay of minerals in Europa's metallic core, which generates heat that affects tectonic activity on Earth. Indeed, scientists suggest that the thermal ocean causes diapers or upwellings in the surface ice, routinely observed in Europa. The extensive curvilinear fault lines on the surface and the island sifting of ice islands point to the dynamic properties of Europa being influenced by forces able to generate notable heat. Whatever the heat source, once thermal gradients develop, the heat transfer along those gradients, that is, the containment of heat from them, could serve as energy sources. Jupiter generates a strong magnetic field across its main satellites, and the varied gravitational pull is a real, if weak, force. An organism that has evolved the necessary transducing systems could use these forces as energy for different biological purposes. Several years ago, we carefully examined the energy from these sources and concluded, especially in light of the already mentioned energy sources, that neither is sufficiently strong nor efficient enough to meet the energy needs of a living system. Although they are unlikely members of Europa's ecosystem, we mentioned them in line with the book's values of keeping an open-minded attitude to all possibilities, not discounted by science or reason. Later theories are based on the idea that different forms of energy may have evolved from creatures optimizing their use of resources. Often firmly ingrained in its lineage, an organism's energy source sets it apart from all other living entities in terms of its approach to energy extraction. Thus, using an energy-centric taxonomy, we will classify our fictitious species. At the lowest trophic level, producers get their energy from abiotic resources in the surroundings. They will get the first thought. Photoactivated cells. Sunlight-dependent organisms for metabolic energy would be limited to the near-surface environment. Surface temperatures are very low, the illumination at Jupiter's distance is weak, and the constraints imposed by ice on the dimensions of such organisms, which presumably live in small to minute inclusions, suggest that they would mostly be slow-growing microorganisms. Living entities maintained by chemical reactions involving hydrogen reduction generated during the breakdown of water could find refuge in inclusions in the surface ice. They are probably slow-growing bacteria for the same reasons. We will call them radiolytic chemotrophs. We have defined several chemical reactions that might occur in Europa's subsurface ocean. At least equal to the processes themselves are the numbers of species able to thrive from these reactions. On the ocean floor, litho equals rock. Chemolithotrophs may flourish on low iron or other metals. We shall name them hydrogen lithotrophs if the mantle releases hydrogen as the reducing agent. They could be considered sulfur lithotrophs if they get their reductive energy from sulfur. One of the sulfur compounds has this quality. On the other hand, methanogens like Earth's thrive by converting carbon dioxide into methane. We will call them benthic methanogens. Aerobic organisms could live on the ocean surface, where oxygen availability is improved, raising the possibility of oxidation reactions. We will group them as upper-level aerobies. These chemoautotrophs depend on generally dispersed chemical substrates in the organism's surroundings. When there are noticeable gradients, such as the ascent of minerals and reducing agents from the mantle, or the diffusion of oxygen across the ice at the ocean's surface, organisms are likely to occupy areas with higher concentrations of substrates. Organisms would lack the drive to move in search of their chemical nutrients if substrates were widely scattered in horizontal layers. A horizontally compressed matrix of sessile organisms is the most likely configuration for these entities. As a result, mats of benthic lithotrophs and methanogens might cover the ocean floor, while different upper-level aerobes live in the higher strata. To keep their trajectory, kinetotrophs need adhesion to a solid substrate. This helps them to absorb convective energy maximum. Delicate organography. Attached to the substrate could be thin or elongated, reeds-like shapes. As they distort, electric currents passing particular molecules impart tensile potential energy. These molecules then use their stored energy to enable mechanisms to improve metabolism. We will call them benthic reeds here. Through another mechanism, ciliated organisms can capture kinetic energy. As the cilia flex in reaction to the flowing stream, tensile deformation at their base turns into potential chemical energy. The cilia can adopt a pancake-like shape by descending to the ocean floor, benthic ciliates, or rising to the surface. Ionotrophs and osmotrophs. Living entities have to be able to move between areas of high and low solute concentrations to make use of the possible energy supplied by ionic and/or osmotic gradients, 8.4. The distance should be minimal, considering the strong concentration gradients at the ocean floor and surface. Two opposing selective pressures during their evolution make it challenging to estimate the size and shape of these species. A large surface area relative to the volume would boost the ionic or osmotic channels per organism's count. A larger organismal volume would be a more effective buffer against the variations in concentrations resulting from the influx of ions or water. While maximum volume demands the organism remain large and spherical, maximum surface area calls for the organism to be compact and flattened. Evolution could investigate both options, whereby Europa might support microionotrophs and mega-osmotrophs. Thermotrophs are. Should thermal vents exist on Europa's ocean seabed, they could support a biotic population as varied and plentiful as those observed on Earth's thermal vents. At least two channels of heat absorption allow these vents to be. A spherical organism might absorb hot water at the vent's aperture, then migrate to a more extraordinary region where the liberated heat increases the potential energy of molecules using structural, conformational changes or high-energy interactions. We would classify this as a bubble thermotroph. Hot water vacuoles could be moved from the starting point at the collinear to the terminal point of the collinear structure over a long length. At this point, heat moves to the cooler surrounding area, providing energy to suitably arranged molecules or chemical bonds. Unicellular photoautotrophs may help heterotrophs, including benthic and thermotrophs, and provide food for symbionts or parasites living on or inside their hosts. Many cohabitants would be tiny and motionless, like algae in lichens and parasitic protists in animals that stay merged into their hosts. On the other hand, if nutrients are abundant, they could develop dramatically and resemble tree fungus or intestinal parasites. We can thus classify them based on size and host, such as microthermatogenic scum or megachematrophic suckers. Small motile species, such as snails that graze on the biofilm of bacteria, protists, and smaller metazoans living on the substrate, may find food from stationary producers. We could differentiate between benthic and sealing scrapers, assuming organic coatings surround the floor and the ceiling. Mobile and pelagic predators could be preyed upon by mobile producers, including bubble thermotrophs, benthic ionotrophs, and sealing osmotrophs. Analogues for the waters of Earth are active swimmers like small fish and floating, lifelike jellyfish. We shall classify them as flotation catchers and mobile catchers. We also picture fan-shaped constructions, akin to those of the fan coral in Earth's marine environments. We could fix them to the ocean floor, so their planar surfaces run perpendicular to the tidal flow. This direction would improve their ability to gather trash carried by the stream and microscopic life. We will call them floor fans here. Like giant fish eating smaller fish, These primary consumers could be hunted by larger, though fewer, secondary consumers. The number of predators could match the diversity of their prey. For simplicity's sake, we shall classify them as tertiary separators. Your surroundings include decomposers, a type of consumer that feeds on dead and broken down organic matter. When a species dies, it falls to the ocean floor and is broken down by detritivores, from tiny bacteria to lobster-like species. Thus, detritivores usually gather on the ocean floor. Hence, they will be called benthic micro-scavengers, or detritivores. Scavengers, detritivores. Two main phases can define Europa's past. 1. An early phase of uncertain length, most likely short, marked by liquid water enveloping the surface and a solid silicate mantle encasing a solidified metallic core. And 2. A later, protracted phase defined by a frozen surface, beneath which sits a layer of liquid water above the solid mantle and under the outer icy crust. Residual heat from the formation of the satellite would have caused enough evaporation from the liquid ocean in the first phase to produce a water-vapor atmosphere. Through the radiolytic breakdown of water molecules, the significant radiation from Jupiter and, to a lesser degree, the Sun would have generated more oxygen than what happened in Earth's primordial atmosphere. Later, as the ocean froze, intermittent significant impacts could have melted the cold oceanic crust, quickly producing a freshwater vapor atmosphere that evaporated as the ocean surface refroze. Given this planetary past, we have sketched a possible evolutionary path for hypothetical life on Europa. The numbers in the picture match the mentioned evolutionary phases. There is no reason to doubt the possibility that life may have started in this first phase. Accretion produced significant heat and organic compounds from the circumstellar disk, and meteorites were readily available when the global ocean was in a liquid form. Basic chemoheterotrophs. Primitive life forms fed on easily available organic compounds. Later on, other energy-based mechanisms could have developed, including ion reduction. Sunlight would have been strong enough at the ocean's surface under an early water-vapor atmosphere to support the evolution of simple organisms using photosynthesis. One could imagine a photoautotroph developing into more complex cellular structures akin to algae. Large osmotrophs, or microbial ionotrophs, step 9, could have obtained their energy from osmotic and ionic gradients. Osmotrophs may have been facilitated by thermal emissions from the oceanic substrate. After the earliest producers had developed, they may have provided sustenance for a primordial leading consumer. The emergence of higher-order consumers may have proliferated from these original essential consumers. Once the ice shell solidified, two separate interfaces with water would have been accessible for colonization. Under the ocean's surface ice, a water-ice contact would offer a solid substrate, while the ocean floor would establish a water rock or sand connection. The vertical separation between the two is expected to be tens, if not hundreds, of kilometers, rendering the two ecosystems independent biospheres. After the formation of the ice shell, creatures resembling algae may have remained enough near the surface to obtain nourishment from sunlight, or to undergo radioactive decomposition of hydrogen to synthesize high-energy molecules. A new producer form may have developed to extract kinetic energy from water currents at the roof or ocean floor. Variations on this theme may have included reed-like organisms or filter-feeding fan-like organisms. A progenitor of the heterotrophic producer may have been an anaerobe, which subsequently evolved into an aerobic organism that utilizes oxygen near the surface. Certain life forms may have persisted in a tertiary, more miniature biosphere. This could have happened on the surface, termed surface face, where water rising from under or bolide impacts from above might create transient pools of liquid above the ice in a water-vapor environment or in liquid inclusions, cryptobiotic. Nowadays, A wide range of organisms thrive on the ocean floor and sealing so that consumers may scrape them from these surfaces and let different parasitic or commensal species flourish. Around the floor and ceiling, a floating way of life would have evolved. Progeny of these passive feeders would have produced more critical variations. Mobile consumers could have developed, which would have raised expectations and levels. Emerging to eat broken-down waste gathered on the ocean floor or across the oceanic depths up to the surface are detritivores. We presume that every living form shown has continued into the present. The trophic structure of the system defines its energy flow. Comprising just producers who absorb carbon dioxide and use hydrogen emitted from the surroundings to extract energy from the environment, it is a basic multi-level ecology. The biomass of every trophic level corresponds to trophic zones. As explained in Chapter 3, the inefficacy of energy transfer causes each next trophic level to have less biomass than the one before it. Far less than 100%. As computed before, the energy conversion efficiency of species on Europa is still unknown. The minimum size a live organism can reach is still unknown. Nevertheless, claiming that it is probably tiny, especially concerning the goods discovered on Europa, is logical. This is untrue on Earth, where sunlight helps plants grow significantly. Still, most of the biological production on Earth comes from microorganisms in the top strata of the ocean. If a highly plentiful energy source exists on Europa, massive producers could live there. Animals have evolved to make the most use of it. Although assurance is impossible, most energy sources are less suited for efficient capture than sunlight. Thus, it is reasonable to expect that Europa's total energy output will be relatively low. The total biomass that can be maintained depends on the availability of general energy. Using logical presumptions on the dimensions of animals at each trophic level in comparable marine environments on Earth, we can estimate the quantities and sizes of organisms at each trophic level in model ecosystems for Europa. We have tried to replicate Europa's energy availability and resulting biomass. The computations are difficult and full of presumptions based on our current knowledge, which are educated guesses. The results of these simulations are instructive in helping us grasp the features and limits of possible life on Europa. Christopher Chiba and Cynthia Phillips of the SETI Institute are presenting a model ecosystem based on radiolytic oxygen generation at Europa's surface. Depending on the oxygen flow into the subsurface ocean under the ice, researchers found that a tertiary consumer weighing about 1 gram, akin to a tadpole, may occupy every 6.76 cubic meters of water on Europa. This would happen if we evenly scattered the biomass over the sea. Based on methanogenic producers, we have proposed a model ecosystem with a boundary length of 5.7 meters that generates biomass equivalent to that of tertiary consumers over every 32.5 kilometers of the sea. The third model ecosystem, presented by Mikhail Zolotov and Everett Schock, uses anaerobic sulfate reduction as an energy source. Their results show that a tertiary consumer in 729 cubic kilometers of water is roughly a cube with 27-kilometer edges. The different expected densities for apex species in Europa's ocean result from different presumptions about producers' energy sources. We're not sure which of these models' approaches are practical. They help one to see possibilities, including the restrictions on support for every environment. It seems unlikely that animals the size of tadpoles, scattered over an average distance of 27 kilometers, as suggested in the model of Zolotov and Schock, form a viable population. On the other hand, the same creatures could interact readily at an average distance of 5.7 meters, roughly the length of a household swimming pool. Knowing habitats and likely energy sources and counting a possible range of species, we can imagine the biotic communities on Europa. 3 separate living zones exist. The first and most speculative theory holds a colony of life close to the outer surface of the ice. If life is found in the subterranean ocean, the other two most likely live at the junction of the sea surface, the roof line, and the sea floor to mantle boundary. Unprotected species on Europa's surface face significant challenges from the intense radiation and frigidity. Still, a stratum of phototrophic organisms could likely live in slight liquid inclusions in the ice, a few millimeters from the surface. We have further non-phototrophic, phototrophic, and non-phototrophic organisms affected by hydrogen ion gradients generated by radiative surfaces. The small size of the inclusions would limit the organisms to microbial scale, and their access to energy sources would be limited to horizontal layers, successive to but not at the ice surface. This community would show up as horizontal strata in cross-sections of ice cores. When we come upon the ice, we can see mats and film ciliates, ciliated organisms that depend on adhesion to a substrate, proliferating. Grazing would entail different symbionts, snail-like detritivores, and scraping behavior among these flat populations. The creatures near the roof might be somatotrophs, whose size varies depending on their adaptations for negotiating the salinity gradient. The ocean floor might look like this, with mats and films covering the whole horizontal substrate, mostly made of chemoautotrophs. The organismal variation of this benthic community could be much enhanced by a wide range of symbionts, consumers, and decomposers. Rising above the sea, ionotrophs can pick and release ions from the seabed into the less concentrated waters above. On the lions, several secondary consumers can swim and dine. It is more difficult to predict the features of the creatures, living in the open depths between floor and ceiling. Predators could use this space for food any time any organism enters it. Together with the number of trophic levels in the food chain, the dimensions and mobility of these consumers depend finally on the overall energy absorbed by the producers. The most crucial piece of information about Europa is the availability of energy. Apart from a layer of microorganisms, Europa's main biosphere would be limited deep under the satellite's surface, under continuous darkness and cold. Under metabons, what would living mean? Should life take place in Europe, it would grow and change slowly. Europa's lithospheric core's small size limits radiogenic heating. Thus, any energy gained from convection currents must be used by organisms to remain fixed and motionless. Ionic and osmotic gradients have great promise, but either delayed flotation or elongated organisms clinging to the surface could absorb them. Organisms are expected to live in cold conditions, have limited energy stores, and seldom need autonomous locomotion. Because Europa uses strategies akin to plants, its biomass is stationary and resembles that of plants. Forecasting the importance of sexual reproduction on Europa presents a difficult task. On the one hand, Europa's geological past has remained essentially unaltered since the world ocean solidified soon after its birth. This would have prioritized stabilizing selection in early planetary history, improving the most basic and effective reproductive mechanisms. Usually speaking, this relates to essential fission, budding, or another vegetative form of asexual reproduction. On the other hand, Europa's biological dynamics were much influenced by parasitism. Sexual reproduction could also be necessary on Europa, since several theories of sexual reproduction on Earth propose its primary purpose is to minimize the adverse effects of parasitism. Still, even sexual reproduction would mimic that of plants, with reproductive cells distributed passively. For most of the biomass is expected to remain stationary. Motile organisms in Europa's ocean would need autonomous movement, since their chemical, osmotic or kinetic energy sources are universally available at the interface between the sea and substrate where they mostly live. Thermotrophs would do so passively from their stationary heat sources, requiring little movement, perhaps only short distances. like evolution has driven the cheetah and elk to maximize their speed over time. The evolutionary rivalry between predators and prey drives both to optimize their speed as one advances up the food chain. The availability of energy could limit some life forms. Most living forms on Europa are unlikely to have ordered sensory systems. Most species are expected to be stationary or passive drifters in a deep, dark oceanic habitat. Their local environments may be reacted upon by encasing them in salt concentrations, furthermore suggesting their capacity to expand or migrate toward energy sources, such as concentrations of hydrogen ions. They could also exhibit trophic amoeboid behavior. They are thus like terrestrial plants and microorganisms in this sense. On the other hand, sensory experience and particular evaluations guarantee that consumers can feed themselves. Though the power to detect electrical currents, thermal variations, and chemical substances, odors, would be beneficial, this sensory ability would exclude vision. Europa's underwater habitats are expected to be devoid of sound and light, since it is unlikely that large organisms able for long-distance acoustic communication would find home in these areas. Still, some consumers could use sonar to find prey, or can see gas bubbles coming from deep-sea vents. Sensitivity to pressure, heat, odor, and possible auditory perception would call for a nervous system-like mechanism. It is not very difficult to find whether animals living in Europa's subsurface ocean have the cognitive capacity to absorb knowledge and show behavior in line with decisions. Furthermore, it is challenging to determine whether these species have sensory capacity and mobility. Terrestrial animals' cognitive capacity is directly correlated with the complexity of their neural systems, which is shaped by their range of sensory activities and the requirement of motor coordination. Should our theory, that most animals in Europa's ocean are essentially motionless and devoid of sophisticated sensory capacity, be validated, we can deduce that even the most intelligent entities in such an environment most certainly have limited cognitive capacity. Europa might have alien life. Still, such intelligence is not particularly sophisticated. We cannot write off the idea that Europa is dead. Europa's mantle and core are smaller than the Moon's, which suggests that Europa might not have any residual internal heat source, since its lack of radioactive decay produces internal heat. Europa's nootropic metabolism makes no compounds like carbon dioxide or sulfur. Underneath the ice layer, there could be an eruptive ocean. As such, no currents or other kind of kinetic energy could be reachable. In the end, even if we might have imagined a planetary past for Europa, this is untrue. The length of time the liquid water layer covered the rocky core might not have been enough for life to start. Any one of these possibilities, if accurate, would reduce the possibility of life on Europa. The young and active surface suggests notable tidal flexing. This guarantees energy capture for species with appropriate adaptations, thermal, kinetic, or both, even if it would only involve surface chemical sampling and geological activity. Measurement. A robotic trip to Europa would significantly improve our ability to determine the viability of different scenarios. Europa's reality is more accurately reflected by a dynamic, multi-layered ecology growing under its frigid surface than by a barren, frozen entity. Our discussion of the possibilities for life on Europa also has to include the same ones on a more far-off moon. Enceladus, the small ice satellite of Saturn, the cryogenic moon. Enceladus defies our expectations in several respects, especially considering that a celestial body of its small scale, about 500 kilometers, should remain cold after 4.5 billion years since its birth. Unlike this expectation, Enceladus radiates thermal energy from its southern pole and shows traces of recent resurfacing. Approaching within 25 kilometers of Enceladus in November 200, the Cassini orbiter produced terrific images of jet-like plumes from its south pole. Examining the South Pole more closely revealed the clear trenches known as tiger stripes. Scientists also discovered evidence suggesting that the geysers and thermal activity come from separate fractures along these stripes, now recognized as slide faults in the unforgiving frozen crust. Different theories abound for the energy driving the geysers. The compositional data show that the geysers' contents mainly consist of water and methane, and trace amounts of organic compounds, nitrogen, carbon dioxide, and carbon monoxide. According to experts, these emissions mainly produce Saturn's E-ring, and sodium compounds within the ring most likely come from water beneath the frozen crust in touch with a rocky core. There is an unmistakable resemblance to Europa, given the possible presence of liquid water under Enceladus's surface, and the availability of heat and possibly organic chemistry. Forecasts on the potential presence of life there follow the same logic and reasoning already discussed for Europa. One unresolved question relates to the historical course of life under Enceladus's ice. During their formative years, Saturn's largest moons, Titan and Enceladus, might have had similar warmth and a relatively plentiful array of organic compounds. The two could have traded simple forms of life. Given its small size and great distance from the Sun, Enceladus froze quickly. Any beginning of life based on the existence of liquid water at the surface would demand a relatively quick happening. Still, given Enceladus has defied conventional wisdom, we should not rule out this possibility. Should life have started or arrived in Enceladus's primordial era, the biosphere could have stayed. For three reasons, Europa is rather important in the thinking of astrobiologists. At first, our solar system acts as a reference. In such case, Europa could be more typical for a planetary body in the universe than our inner rocky planets or gas giants, since little icy planetoids are the most common objects in our spatial proximity. Second, Europa is probably home to life forms. Human explorers are more suited to find since it has plenty of water. Though they're mostly different beginnings, the early life forms on Europa have a planetary history similar to Earth's formative period and may show traits of our primordial organisms. In essence, a planet with a different interior and an ice-covered ocean can support a great variety of habitats. This suggests, from the history of life on Earth, that many energy sources and varied environments are absolutely essential for promoting biological diversity. With the likely exception of Titan and Triton, Europa shows a higher potential for biodiversity based just on this assessment than any place in our solar system. Enceladus is less likely to support life than Europa given its small scale and distance. The unanticipated geophysical activity in that area makes us question accepted wisdom. Strong evidence of life on Enceladus points to most likely existence on several other celestial bodies within our solar system. Beyond Earth, Europa is the most likely place in our solar system where a rather sophisticated biosphere, including life forms like those we know, can survive. It has many energy sources and a sizable subterranean ocean of liquid water. There is no reason to doubt the possible presence of organic chemistry precursors, even if the chemical richness of the oceanic ecosystem is yet unknown. Additionally, enveloping the ice shell of the ocean is a delicate oxygen atmosphere, which might support subterranean habitat. On Europa, light serves no biological purpose except for a small population of ice-encased organisms at the surface. All other life forms are surrounded by many kilometers of light-obscuring ice. Underneath the ice, energy can come from chemical reactions, heat emissions from within, water currents, ionic or osmotic gradients produced by the ocean floor or ice ceiling, respectively. Different producers, depending on any or all of these energy sources, could create the basis of a food chain able to reach great complexity. With species similar in scale to the small to medium-sized marine fauna known on Earth, reasonable models have been proposed that show ecosystems reaching the level of tertiary consumers. On Europa, life is supposed to be mostly sedentary, marked by little mobility resulting from cold conditions and limited energy availability. This suggests limited cognitive ability and basic sensory systems. The simple stressing the sexual interaction of genetic material would be the reproductive strategy. We could have preferred to eliminate the parasite entrance. Europa's possible importance among the planets in the universe, its ability to sustain water-based life forms which may resemble those on Earth, and its clear demarcations between water, ice, atmosphere, and substrate enable the habitat fragmentation necessary for the emergence of complex biospheres. Thus, researchers are eager to investigate extraterrestrial life. Europa has excellent potential for biodiversity, much as any other known extraterrestrial planet. At last, we also briefly consider the small frozen planet Enceladus. Like Europa, the water jets emanating from its southern pole suggest the existence of a sizable oceanic reserve under the surface. Given confirmation, the debates in this chapter on Europa would also apply to Enceladus. Existence on a turbulent, sulfur-filled lake at the nexus of volcanic heat and frozen terrain. 4 years earlier, La Morabito had graduated with an astronomy degree and started working as a navigation engineer for the Voyager mission. Voyager 1 approached Io closest on March 5, 1979, gathering pictures revealing a celestial body never seen in the solar system. Ensuring Voyager stayed on its proper course, Linda's task was to precisely ascertain the positions of her target planets and moons relative to the stellar backdrop seen from the spacecraft. She was enhancing the contrast of an image taken the previous day to identify the weak stars hidden by Io, when a crescent-shaped object emerged in the top left edge of the Moon early on March 9th. Understanding that such a large object could not be another moon in that location, she realized she might be seeing something never seen before. When one considers the discovery years later, the thrill had not lessened. Every astronomer and planetary scientist expected such a large object. It seems impossible that such a significant object had ever gone unseen. Those events were truly amazing. Linda and her associates looked at every logical justification for the aberrant image for the next 6 hours, until only one possibility remained. Months earlier, Stanton Peele and his colleagues at the University of California, Santa Barbara had issued a prediction indicating that Io should show volcanic activity. It became increasingly clear that Linda had seen the nebulous plume of a significant volcanic eruption. The crescent form and the luminous region at the terminator, the demarcation between light and shadow, probably result from surface events on Io. That evening at dinner with her parents, her father said, "Are you aware that you might have found the first volcanic activity outside of Earth?" Her discovery profoundly changed her. "It was delightful to hear him express that," Linda said. Shortly later, Linda Morabito's father revealed the finding. Science verified and published it on June 1st, 1979. For many planetary scientists, this represents the most important discovery made during the Voyager mission. Volcanism defines Io now as well. Any process or phenomena connected with that satellite, including its astrobiological potential, starts with realizing that Io is the most volcanically active celestial body known to humans in the universe. Io suffers from its surroundings. Its existence has seen many meteorite strikes, strong magnetic fields, and major gravitational stress, above that of any other celestial body. Its proximity to Jupiter and location between Jupiter and 3 firm friends lead to this situation. It expects understanding of exoplanets in near orbits around their central stars. We can closely watch its daily struggles to assess the limits of life's flexibility. The densest of the leading solar system satellites, Io resembles a rocky planet more than any other. About 1/3 to half of its radius consists in an iron or iron silicate core. Silicates predominate among the remaining elements, much as on rocky planets, suggesting the presence of considerable liquid either beneath or inside the crust, which is estimated to be up to 11 kilometers thick. The density of this planet is much lower than that of Earth. Internal heat of Io is explained by 3 energy sources. First of all, the great mass of the core makes continuous radioactive decay possible, producing thermal energy. Bolide impacts have caused heat to build since Io formed. Nestled at the end of the funnel, drawing in falling bodies toward a collision with Jupiter, it is the closest of Jupiter's 4 main moons. Io has thus probably intercepted a disproportionate amount of impactors. Callisto, the most far-off Jovian moon, has a highly cratered surface that shows the greatly more bombardment Io has gone through over its history. Io's primary heat source is gravitational flexing, which comes from its location sandwiched between the 3 surrounding moons and the giant Jupiter. Io feels gravitational attraction only toward the other moons when it's positioned opposite Jupiter. On the other hand, Io stretches in both directions between Jupiter and its siblings, especially Europa and Ganymede. Scientists believe the expansions and contraction of the rigid crust can have an amplitude of up to 100 meters. With Io orbiting Jupiter every 1.77 days in a 2-to-1 resonance with Europa's 3.55-day orbital period, the surface undergoes crustal tides roughly every 43 hours, except from Ganymede's influence. These differences cause internal friction, so sustaining a constant state of thermal agitation inside. With 1 to 2 dozen active eruptions, enough massive to be seen from orbit, volcanic activity is regularly observable on Io at any moment. Linda Morabito first noted the large plumes expelled with great force at velocities almost 1 kilometer per second. Like the red circle around Pele, this phenomena produces sulfur dioxide, SO2, fountains and other volatile gases ascending to altitudes of up to 300 kilometers, before descending to the surface in concentric rings. Rising subsurface pressures that preserve SO2 and other volatile gases in a liquid form until a surface breach provides an escape path are thought to produce these plumes. The slow movement of lava over sulfur dioxide snowfields generates plumes. Low temperatures cause erupting lava to solidify quickly at the surface, so causing slow migration of the liquid edge of the eruption. Models suggest that the subterranean magma reservoirs might be rootless without a single conduit to the surface. Extremely hot lava melts the crust it passes to create a boundary layer slurry that vaporizes as the erupting seam slowly moves across sulfur dioxide fields, generating wandering plumes. The depletion of significant subterranean reservoirs causes the expanding lava to finally create calderas, crusted lava lakes, and extensive lava fields. The high temperatures approaching 1700 degrees Celsius recorded during these eruptions match silicates rich in magnesium and a considerable concentration of sulfur compounds. There is instead a lot of expelled stuff. Expanded over almost 300 kilometers, the Amirani lava field results from lava expelled at an estimated rate of 100 tons per second. The relative lack of big volcanic mountains on Io suggests that the lava has low viscosity, in line with a high liquid content. Io's environment is quite empty. Mainly sulfur dioxide, SO2. It also contains trace amounts of sulfur monoxide, SO, hydrogen sulfide, H2S, carbon monoxide, CO, and carbon dioxide, CO2. Whether atmospheric S, Utsiansen-Tortu, Baisu comes mostly from direct volcanic emissions of SO2 or from evaporation of surface SO2 is yet unknown. Ionosphere of Io contains analogues of these molecules. Jupiter's intense magnetic field most certainly generates these compounds by extracting electrons from their parent molecules. Condensed SO2 encircles silicate and sulfur compound that make up Io's surface. Different sulfur compounds are supposed to be involved in the echinotechny coloration. Condensed SO2 is primarily responsible for the surface's white color. Despite Io's intense bombardment, its surface stays constantly young thanks to continuous volcanic activity rejuvenating it. Among the solar system's celestial bodies, none has experienced as many changes as Io. There are many different boundaries. On a grand scale, expansive lava fields, multi-tiered calderas, and thin channels cross excellent level plains. Recently laid areas sometimes abut flat, undulating plains, compressed by mysterious forces, overlaying older solidified flows with more detail. Except a few shield volcanoes, Io's mountains have non-volcanic origin. They develop from uplift along thrust fault lines generated inside by compressional pressures. Rising from the nearby level plains, jagged crustal blocks. Although erosional forces from flowing lava also play a part, gorges that cross these mountains are thought to provide additional evidence of these fault lines. There is much evidence of sapping, 9.3. We also discover long channels arising from either liquid flow or sapping. Any liquid flows must mostly be lava, since none liquids can remain stable at the temperature and pressure conditions on Io's surface. Apart from regions of volcanic activity, Io's natural surface temperature is about 90 degrees Kelvin, minus 183 degrees Celsius. This very low temperature reveals Io's distance from the Sun and its negligible atmospheric presence. Volcanic activity causes many hotspots on Io's surface where temperatures rise in concentric gradients toward them. At Loki Patera, Io's most active volcano, temperatures there approach 0 degrees Celsius, the melting point of water ice, at the edge of an oval measuring 50 kilometers long. Surface temperatures can reach 47 degrees Celsius within several kilometers of the hotspot, and may soar to 2,000 degrees Celsius at the site of magma eruption. The generated thermal gradients at the surface can be highly compressed or quite broad. At Loki Patera, for example, the surface temperature ranges from 280 degrees Kelvin, 7 degrees Celsius, to 320 degrees Kelvin, 47 degrees Celsius, across almost 32 kilometers, 20 miles, to the left of the peak. On the other hand, the exact change happens far more quickly, across roughly 1 kilometer, to the right of the peak. Though they have not been measured, similar gradients most certainly exist underneath. As lava, above 1500 degrees Celsius, runs over a snowfield of frozen sulfur dioxide at negative 80 degrees Celsius, strong thermal gradients will be generated. Observations show that this movement moves several centimeters every day. The gradient thus moves gradually. The lava fields could last for long times. Once the surface freezes, insulating the molten lava under will heat the underlying ground and cause a notable thermal gradient in the field's peripheries for a reasonable length of time. Gradients, both horizontal and vertical, will show a constantly changing profile. Io revolves inside Jupiter's magnetosphere, which produces and then removes ions from Io's ionosphere. With Jupiter's quick rotation of its gravitational field generating strong currents estimated at 1,000 gigabytes, a potential electromotive force of 400 kilovolts results. Intense oxidizing action of these ions helps oxidation reduction cycles to be facilitated. Still, most of these ions probably live in the ionosphere, where Jupiter's spinning magnetosphere quickly strips them away, so casting doubt on their role in surface oxidation reduction cycles. Apart from the atmospheres of the gas giant planets, electromagnetism and electricity indicate possible energy sources, maybe to a more extent on Io than in any other place inside the solar system. The combination of silicates and metals most certainly solidified from similar material, forming a much larger core at Jupiter's center. Gravitational flexing would have mostly affected Io's properties from the beginning because of its proximity to Jupiter and position inside the orbits of other surrounding satellites. Jupiter's strong gravitational field drew hydrogen and helium fast to Io's small core. Still, its core was enough big to hold water, which it might have had momentarily during its early years. Sublimation, vaporization from ongoing volcanic activity, and strong bolide bombardment into Jupiter's dense gravitational well caused relative rapid loss of the water. Although Io's interior constantly emits volatile gases, strong magnetic and radiation fields and frequent bolide impacts would have prevented the development of an atmosphere in its early years. Io preserves only a weak atmosphere, mostly consisting of sulfur dioxide and trace amounts of other volatiles. Early in Io's history, its surface temperature dropped to almost minus 180 degrees Celsius, without the thermal insulation an atmosphere offers. Still, friction from gravitational flexing has kept the interior hot, which is then transferred to the surface via focused and dynamic outlets. There is no evidence to challenge Io's vivid colors existing long before human eyes developed to see them. As molten lava moves across an icy layer of silicates and frozen SO2, Io's surface has most certainly changed constantly, for at least 1 billion years. Fire and ice have a contrast that goes beyond simple metaphor for Io. The essential character of life there depends on the interaction between heat and cold. Cold, which denotes the extremes that define a boundary, varying in thickness from millimeters to kilometers, between a frigid substrate too cold for any liquid and a layer of spreading heat that makes almost any liquid impossible. When a temporary balance between fire and ice exists between great heat and the frozen substrate, life may flourish momentarily. Interactions abound in life, between air and surface, sea and shore, ocean floor. Extremophiles live mainly at the extremes of extremes. Although similar sites exist worldwide, Yellowstone National Park best illustrates this phenomena. The many geysers, fumaroles, and thermal pools in the park show too hot, acidic, or alkaline surroundings for species used to more moderate temperatures. Still, some extremophiles thrive in these hostile environments and cannot survive outside of them. Just a few centimeters from the boiling water, these extremophiles are replaced by other life forms fit for the more moderate conditions above or beyond the water's edge. 1 to 2 meters usually allow one to see several gradations of life. Anywhere gradients arise, specific life forms occupy their appropriate habitats. This is clear in vertical and horizontal transitions. A cliff revealing consecutive soil layers, 9.10, shows this. Many people hold the view that life could flourish on Earth. The most reasonable conclusion is that in 1998, he stated that Io possesses neither water nor life. Planetary scientist Bruce Jakosky of the University of Colorado says from a common standpoint. Could alternative solvents exist within the dynamic gradients on Io? Are there sufficient conditions for life that could challenge the prevalent belief that life on Io is improbable? Let us investigate the possibilities. No evidence exists for minimal water on Io. Although the minimum water on the surface indicates that water is an improbable solvent for any substance on Io, sulfur dioxide and hydrogen sulfide show excellent solubility in water. Subsurface water may exist as a liquid near geothermal hotspots, or lava flows if concentrated solutions of these gases, mostly diluted sulfurous and sulfuric acid, are present, reducing water's melting point. Although the low vapor pressure at the surface would lead to fast vaporization, subterranean CO2 remains liquid under pressure in stable reservoirs. Sulfur oxide presents a more favorable option. It is plentiful in its frozen form on the surface, but transitions to a liquid state underground at temperatures ranging from -75 degrees Celsius to -10 degrees Celsius. This corresponds to roughly the 200 degrees Kelvin to 260 degrees Kelvin isobars in Figure 9.8b, covering extensive areas, essentially the dark terrain in the image, with a liquid temperature range of -85 degrees Celsius to -60 degrees Celsius. Hydrogen sulfide could theoretically operate as a solvent. Hence, it could exist as a liquid underground in a geothermal hotspot. However, its surface abundance is much less than that of SO2, which appears to be a more common solvent. This scenario may arise when the solvent in the surrounding environment diverges from the liquid medium in which metabolic processes transpire. While sulfur dioxide can engage in biochemical interactions, it is not an optimal solvent due to its limited capacity to form hydrogen bonds and inability to facilitate the conformational changes of macromolecules essential for their functions. Conversely, hydrogen sulfide possesses these advantageous properties, but is significantly less prevalent. Nevertheless, its liquid range -60 degrees Celsius to -85 degrees Celsius coincides with that of sulfur dioxide. Living cells could utilize TSO ore as a solvent internally, while existing in an environment predominantly composed of liquid SO2. Any potential basis for life on Io would necessitate the ability to synthesize complex biomolecules capable of sustaining metabolic processes in liquid sulfur dioxide, or sulfur dioxide sulfide, at 180 degrees Celsius, temperatures ranging from -50 degrees to -70 degrees Celsius. Our understanding of the biochemistry of carbon-based polymers under such extreme conditions, which diverge significantly from the water-based biochemistry at elevated temperatures that we are accustomed to, is insufficient to ascertain whether life on Io could be constituted from carbon backbone compounds. Currently, there is no evidence of organic compounds, and the presence of carbon is minimal, limited to trace amounts of CO and CO. Sulfur is relatively plentiful. One of the most attractive properties of sulfur as a possible biomolecule component is its capacity to adopt several oxidation states, including fractional ones. This lets sulfur create a great variety of molecules. Sulfur shows several ring configurations, some of which help Io's surface to be vibrantly colored. Investigating beyond the surface and combining liquid SO2 with SO22, one may find chemical complexity involving sulfur rings or polymers. Carbon, sulfur, nitrogen, oxygen, and phosphorus polymers could produce biomolecules like those seen in terrestrial living cells. Still, we have little evidence about the possibilities under Ionian settings, and no proof of their existence. Like many fields of astrobiology, empirical studies carried out in terrestrial chemical laboratories support the theory that this energy type may be unique since it is visible in motion. It is plentiful, and its easily accessible sink created by the opposing freezing ambient temperatures guarantees heat transfer from its source. As Chapter 2 shows, energy moving through a system usually helps it be organized. Although heat is easily dissipated by increasing entropy, making it highly inefficient, its great availability on Io could help life exist there. One rather important source of energy is chemistry involving energy iodation reduction. On Io, sulfur is the main element. It exists in an oxidized state as sulfur dioxide, in a neutral state as sulfur and sulfur X, and a reduced state as hydrogen sulfide. Sulfur thus has theoretically the ability to cycle for oxidation reduction. Whether ionization and reduction events can occur in a way that generates energy, the thermodynamic reality shows that mechanisms have evolved to link with these reactions to harness that energy in a biologically helpful form or substance. Once more, we rely on the inventiveness of evolution. Species change to fit their environment. The record of life on Earth shows that evolution is as creative as our fantasies. A third energy source has to be carefully investigated in the framework of Io for the first time. That speaks to electromagnetism. It moves within the magnetosphere of Jupiter, as was already noted. Although the energy derived from electromagnetism is usually less competitive than chemical or light energy on Earth, Jupiter's magnetic field is at least 12 times stronger than that of Earth, and the sunlight is 20–25 times weaker, suggesting that magnetism could perhaps energize a suitably designed biological process on Io. Furthermore, generating electricity could be Jupiter's magnetosphere's constant spinning along Io's orbital path. Earthly life has developed to sense magnetic fields and electric currents. Sensation naturally follows that energy fluctuations can affect biological processes, since it only identifies biologically relevant energy fluctuations. By connecting energy to a storage mechanism, biological entities could seize it. Unlike the other planetary bodies we've studied, Mars, Venus, and Earth, where the beginning of life was more likely than its survival, Io presents a great challenge. A modern microorganism could easily remain in a state of cryptobiotic hibernation within a frozen substrate until an above-lava flow melts its subterranean environment, revitalizing it. Understanding how those bacteria could have first started is much more difficult. The problem is that we know shockingly little about the first phases of Io's existence. According to the evidence, it could not hold enough water for an extended period, or have an atmosphere for more than a brief interval, before being overwhelmed by constant impacts from celestial bodies and significant gravitational distortions. Concluding that conditions have become too arid, frigid, and fast for the slow processes related to the evolution of life in aquatic environments is tempting. In an abstract sense, we are unsure about the time needed for life to start. Also, we do not know whether the environment fit for the beginning of life on Io stayed long enough. Imagine water as ephemeral, maybe non-existent. Life surfaced in cold sulfur dioxide lakes. Under a thin atmosphere, SO2 could have been scattered over the surface during a primordial phase of Io's existence. Although we cannot discount the idea, we lack convincing data and strong models to support it. Given our ignorance of the source of life on Earth, the acceptance of our uncertainty about its possible beginning on Io should not be taken as a sign of a significant weakness. This book emphasizes possibilities rather than historical facts. Thus, we will now suggest that life could have started on Io despite the chaos and violence around the formation of the satellite. Any surface environment fit for life on Io was fleeting. Researchers hypothesize that Io and Europa began at either -23°C or higher, 8. This suggests that given enough atmospheric pressure to prevent evaporation, the surface might have harbors of liquid SO2 and SO2–SLOH2S following the freezing of any water, perhaps on the substrate at the bottom or in small puddles where evaporation concentrates vital reactants. These pools may have endured sufficiently for life to develop within them. The pools would have either evaporated or frozen as they adjusted to the planet's global average surface temperature, once the atmosphere was eliminated by Jupiter's strong magnetosphere, or eroded by the first bombardment. Underneath the surface, where temperatures and pressure are higher, specific strata would retain temperatures between -10°C and 5°C, which would be appropriate for liquid-form sulfur dioxide retention. The underlying crust formed a rigid, frigid surface from silicates, frozen sulfur dioxide, and other sometimes flowing lava sheets would pass across the frozen ground, momentarily melting it and turning it into a mushy mixture of minerals and solvents. Depending on the volume of lava above, the solidification of the lava and the heat's dissipation, an interval spanning minutes to centuries, would cause it to freeze once more. Its habitats fall into two main groups. One consists of relatively stable subterranean reservoirs, mainly composed of sulfur dioxide. The other consists of transient mixtures of soil and liquid that liquefy at the interface of extreme temperatures, as where geothermal hotspots or flowing lava come across frozen ground. The Earth will thus once more solidify. Although the length of time these two habitats have existed as the only ones on Io is unknown, They have most likely been favorable for life from their beginning. Thus, our hypothetical path for evolution on Io relates to a single geological condition that has existed from the beginning of life on that celestial globe. That's hardly likely to happen. A meteorite might have thrown MS from Europa's frozen surface into the satellite. The European life would meet an environment so very different from its source that survival in the domain of fire and ice seems improbable, even if the ice fragment were sufficiently large to withstand the blast that propelled it, which is dubious. Let us suppose for this hypothetical history that life started on Io, in or under a pool of liquid sulfur dioxide. The first cells might have emerged from enough H2S to facilitate more complex chemical reactions in a safe environment. The first phases of life most likely used molecules condensed in ice inclusions or followed solid substrates as essential elements and energy barriers. They also combined the larger molecules required for whole life. In other words, they would have been ancestral chemoheterotrophs. Chemotrophs fully developed and capable of consistent self-replication could have emerged on substrates under the liquid, step 1, and within tiny cavities in the SaO2 ice above or adjacent to those substrates, step 2. An ancient substrate, thermotroph, would have used the abundance of thermal energy, step 3. Free-floating chemotrophs, step 4, evolved from forebears buried in ice inclusions. Though our repeated observations show that heat is not a suitable basis for bioenergetics, its abundance at the margins of heat sources, such as spreading lava fields, forces us to consider a possible form of life on Io that might have evolved to depend on it. After absorbing heat from a source, such as a substrate, free-floating thermographs use that heat to lower the substance to a liquid temperature. This would have enabled chemical reactions connecting heat transfer and energy harnessing. From another point of view, long thermography, step 6, gathers energy by lowering heat transfer from a heat source at its base inside the substrate to a sink at the terminus of the colder construction. The free-floating autotroph might have evolved the ability for self-propulsion, thus turning into a motile thermotroph, step 7. Apart from the Sun, the strong magnetosphere of the solar system presents a significant energy source. Transitional organisms like a magnetothermograph, step 8, and a magnetochemotroph, step 9, were the first to acquire the ability to use magnetic energy. These might have then developed into completely magnetotropic entities. A mobile magnetograph, step 10, harnesses energy using specialized cellular mechanisms that separate charges. This serves similarly to the thylakoid membranes in plant chloroplasts, which use light energy to retain electrons split from water. One variation of this idea would be reed-shaped magnetotrophs, step 11. Power could have come from the Lorentz force-induced electrical currents along their elongated bodies. Customers might have evolved to eat every variety, with many food producers available. Most likely among the first in this classification were ice grazers, step 12, and substrate grazers, step 13, which eat producers living on ice and substrate respectively. Then creatures with buoyancy, step 14, excellent mobility, eat any available prey, step 15, and only feed on reeds or plant-like organisms that have evolved by that stage, step 16, could have added another level to the food chain. Provided the temperatures stayed sufficiently warm to prevent freezing, life may have flourished in the subterranean lakes of liquid and permeated the ephemeral slurries of the substrate in the constantly changing environment that has always existed. The freezing would happen, though. Early on in life on Io, selection pressure most likely helped cryptic organisms capable of surviving protracted periods of suspended animation evolve until further lava flows or fresh fissures in the crust introduced heat. Hence, awakening. As such, covert forms of magnetotrophs, step 17, thermotrophs, step 18, motile consumers, step 19, and vegetative consumers, step 20. Whereas cryptic detrivores, steps 22, would have developed alongside other cryptobiotic organisms, detrivores, steps 21, would have emerged early in all ecosystems. Whether subterranean lakes of liquid exist as pools inside lava tube caves, or resemble groundwater on Earth, where spatial and habitat fragmentation could help to create a rather complex ecosystem. Their size and duration remain unknown. This challenges the ecological type of prediction. A multi-layer trophic structure could develop if strong and long-lasting liquid-filled subterranean layers exist. Figure 9.11 shows the lowest biodiversity recorded on Io among 11 producers, 5 consumers, 3 of which may occupy a secondary or higher trophic level, and 2 detrivores coexisting. It might be somewhat more all-encompassing than that. Another issue is that the simplification framework may overstate biodiversity and ecological complexity if biochemistry or energy extraction is useless in that environment. The alternative habitat would be much simpler, consisting of cryptic species incorporated into the substrate that activates momentarily. Its existence would be limited to the interstitial voids between grains of sand and soil, just as in all ecosystems. The degree of life at the slushy margins of lava fields and geothermal hotspots would captivate a limited number of microbial producers, and even fewer microbial consumers. The total biomass of every ecosystem is determined by the possible amount of biologically valuable energy that the surroundings could provide. Although Io has plenty of energy, our limited knowledge of its helpful application makes any biomass estimate and implication of ecological complexity on Io speculative. On Io, life in underground pools of liquid sulfur dioxide reflects that of Europa's subsurface ocean, where life is mainly found in the dark, often inhabiting the floor and ceiling of liquid environments. But the similarities stop there. So too is the solvent. It consists of SO2 and H2S, and could be more critical in cells than H2O. This suggests that the macromolecular structures and biochemistry will differ significantly from water-based systems. The temperature is far lower. There is a pretty different energy composition. On Europa, however, a basic need for life on Io is absent. Life can only flourish inside a small thermal window, opening and closing sporadically and unpredictably. Particle emissions from Io's surface interact with Jupiter's strong magnetosphere in a plasma radiation environment that would be fatal even to Earth's most radiation-resistant life forms. Therefore, to preserve macromolecular integrity, any life form has to be highly resistant to harmful radiation. Researching radiation-resistant organisms on Earth could help us to reach this goal. Among the most well-known radiation-resistant bacteria is Deinococcus radium. Natural selection for desiccation resistance has helped it develop resilience to high radioactivity and UV radiation levels, cytotoxic chemicals, heat, and high sound velocities. DNA's toroidal form. Radiodurans' atypically dense and laterally ordered structure helps to explain their resistance to radiation and desiccation. 4 compartments comprise the DNA toroid, each containing a single copy of DNA limited inside the ordered DNA toroid. Furthermore, the DNA is organized in a unique ring that prevents broken DNA generated by radiation exposure from freely spreading inside the cytoplasm. Consequently, unlike other bacteria, by tightly enclosing the cut DNA segments inside a circular structure, radiodurans can preserve broken genetic material. Held close, the pieces finally come together in their exact natural order, rebuilding the DNA strands. 9. It is unknown whether possible Io species have DNA or other like molecules. This comparison looks at radiation resistance on Earth with that on Io. where studies have shown some cellular components can protect against molecular fragmentation, the main hazard Io's higher radiation levels present. Rates will be slow, since they only occur at temperatures much below the water's freezing point. Metabolism only covers the range of -60 degrees Celsius to -75 degrees Celsius, since both sulfur dioxide and sulfur dioxide, 22-sulfur, exist as liquids within this range. The intracellular mechanisms of Ionian organisms depend critically on hydrogen sulfide. In principle, narrow thermal activity ranges have no problem. Birds and mammals restrict their allele metabolism to a small spectrum. This suggests a general expectation of lower reaction rates. It is a prime example of R-selected populations, those defined by ecology. The notation indicates a mathematical model for opportunistic population increase, distinguished by a limited period for reproduction and high death rates. Under suitable conditions, populations subjected to torr-selective pressure reproduce rapidly and expand fast. This phenomenon results from a surge of warmth activating mysterious creatures that suddenly liquefy their surroundings. Though less indicative of persistent subterranean pools, the erratic geological activity on Io could suddenly cause an entire reservoir to erupt and vaporize. R-selected species thus serve in both kinds of habitat. In R-selected populations, reproduction happens quickly. The average size of the offspring is small, and there are rather significant numbers. Natural selection favors accelerated growth rates in habitats not always conducive to development. These form theoretical forecasts. Although all of these remain unknown for possible life on Io, space, food availability, competition levels, and ecological complexity affect real populations' reproductive and growth patterns. Although most possible life forms are microbial, typified by simple, quick asexual reproduction, this conclusion cannot be drawn with certainty. A creature on LO can welcome a conservative viewpoint on energy. Consequently, there are few motile forms, since the low operational temperatures imply a relatively low degree of motility. Most life on Io is likelier to be small and stationary than subsurface life in other environments, excluding deep liquid reservoirs is. Usually, sedentary species are pretty good at sensing their surroundings. Touch, olfaction, and gustation are hence rather important. The sensory attributes necessary for life on Earth are traits of individual cells, even unicellular bacteria, implying that the most primitive organisms have this ability. For an organism neither pursuing goals nor capable of mobility, the sensory modalities for distance perception, vision, and auditory cues are useless. Conversely, motile organisms can always sense information on objects or features in their surroundings from a distance. For the expected limited mobile life forms, photoreception in the subsurface of Io would be useless. But sound or vibration and electromagnetic sense could be significant. To suggest that some species on a planetary body, where most scientists doubt the existence of life, could have some intelligence seems presumptuous. Io's most common life forms are probably bacteria and fungi. They show no obvious intelligence or behavior. Permanent liquid pools may show some intelligence if they contain sufficiently dense and sophisticated ecosystems, including big, mobile secondary or tertiary consumers needing an integrative apparatus like a nervous system. Currently living on Earth, the most intelligent non-hominids and the brainiest animals are marine mammals, distinguished by poor vision but remarkable auditory capacity. Comprising a somewhat lower density than Mars, Io is the fourth largest moon in the solar system. But given the variety of multicolored sulfur compounds released from its relentless volcanic eruptions, it more resembles a pizza than a planet. As it revolves between the great gravitational influence of Jupiter and three significant partners, it experiences gravitational bending unmatched on our planet. The main feature of Io is its remarkable volcanic character. Superheated sulfur compounds explode to heights hundreds of kilometers above the surface, then fall as snow. except in regions where internal heat causes them to melt into beneath liquid pools. A surface temperature of -180 degrees Celsius prevents even sulfur dioxide and sulfur dioxide 2,2-sulfur from remaining solid. At any one moment, at least 12 volcanic hotspots spew lava that melts the nearby ice cover. This creates a secondary fleeting habitat for liquid SO2, MiSO2, to mix with the mineralized crust. If life exists on Io, these two volatile and transient pools of liquid sulfur dioxide are most likely settings for it. Larger molecules would probably include more sulfur, nitrogen, phosphorus, and other components to build their backbones. H2S is more likely to function as a solvent within cells. It would be a life form distinguished from our experience by unusual chemistry, controlled by metabolism, and different structures and functions. It could only flourish in a particular limited temperature range and would exist underground. Still, this could happen, albeit momentarily, in local pools or across small areas of land, whenever a hotspot developed or a lava flow moved. As is the case generally, Io mainly represents an edge effect. The edges are more strongly visible and dynamic than anywhere else in the solar system. This highlights favorable biological features, including quick reproduction, fast development, and the ability to withstand a long period of time in a hidden state of suspended animation. On Io, life reflects the pinnacle of evolution toward cryptobiotic species within our solar system. For further astrobiological study, no one's agenda gives extra priority. Still, it would be wrong to write it off completely. From our terrestrial point of view, scientific logic and reasoning support the possibility of life in such a context. If life materializes there, it will significantly broaden our knowledge of its nature. Except for the next two worlds we will explore, no place provides as much possibility for surprise and delight as the first pictures of this pizza-colored phenomenon Linda Morabito and the rest of us encountered in spring. Petrolates, life in reservoirs of organic liquids like those on Titan. Saturn was the far-off planet in the known solar system in 1655, and the crude telescopes of that age revealed a mystery. Sometimes the Earth seemed to have handles on both sides, and other times the bulges, like hands, disappeared. Born into a wealthy Dutch family of high standing, Christian Huygens was allowed by his father to focus only on his interests in mathematics, mechanics, optics, and astronomy. With a much improved telescope than previous models, he could detect enough detail about far-off planets to postulate that the handles were rings encircling the planet, sometimes seen at an angle towards Earth, and at other times viewed edge-on from Earth, making them undetectable. Huygens observed what he first thought to be a bright star moving in front of and then behind Saturn, roughly in the same plane as the planet during consecutive evenings of viewing her bulges. He rightly deduced that what he saw was the first moon of a planet different from Earth and Jupiter. Originally called Luna Satumi and later renamed Titan, the moon rose to be the sixth known satellite of a planet. Dutch astronomer Gerard Kuiper worked on radar countermeasures in the United States following Galileo's discovery of Earth's surface and Jupiter's 4 moons in the solar system. During World War II, in the late winter of 1943, he decided to take a break working at the recently built McDonald Observatory in the Davis Mountains of West Texas, close to the tiny hamlet of Marfa, which would later become well known for its erratic nocturnal lights of mysterious source. One evening, by accident, several vital satellites in the outer solar system aligned, and he pointed his spectroscope at each one. Suddenly, Titan's spectrum showed a clear signal of methane gas, the first evidence of an atmosphere on a moon. Titan is thus the only celestial planet in the solar system with a nitrogen-rich atmosphere comparable to Earth's, since Titan's atmosphere is mainly composed of nitrogen. The presence of methane, an organic substance possibly suggestive of life, sparked the most intricate and expensive robotic mission in the annals of space exploration. The Cassini-Huygens mission to Saturn and Titan. Titan was first seen by Voyager 1, which took a close-up picture in November 1980 while passing the Saturnian system before the Cassini-Huygens mission launched. It is understated to characterize this anticipated view of Titan as a disappointment. Titan seemed like a homogeneous orange sphere covered in a thick cloud in closest proximity. Its surface was hidden. Based on the blue haze in the upper atmosphere, 10.2 centimeters, which corresponds with the known existence of methane, the smog below was assumed to be a hydrocarbon haze of indeterminate composition. Along with low levels of other hydrocarbons, hydrocyanic acid and nitrites, organic compounds including nitrogen, the atmosphere mainly consists of nitrogen with less methane, ethane, argon, and carbon monoxide. Rising to a height above 100 kilometers, it creates an air column. Based on solar abundance predictions, we find a higher frequency of the heavy nitrogen isotope, 15N2, than expected. Titan's primordial atmosphere was denser and more significant than it is now at high altitudes, since lighter isotopes prefer to escape into space over time. UV light and ionizing radiation form reactive molecules from methane and nitrogen. More importantly, these molecules form organic compounds like benzene and polycyclic aromatic hydrocarbons, PAHs. The technique produces rather large ionized organic molecules. They can generate tholins and complex hydrocarbon-nitrile complexes 3 in concert with benzene and PAHs. These finally fall to lower, more unusual layers of the atmosphere, where they gather to form a haze reminiscent of smog. At altitudes between 30 and 50 kilometers, ethane and methane produce locally common clouds, which may be caused by methane outgassing from the interior. The surface temperature runs about minus 180 degrees Celsius, 292 degrees Fahrenheit. Though water ice makes up a sizable portion of Titan's mass, at that temperature, ice seems somewhat similar to rock and has the hardness of such, 10.3 billion. Still, methane and ethane can remain liquid on the surface at such pressures and temperatures. They gather in basins after descending to the lower, calmer sections of the sky, coalescing into droplets of organic liquids and precipitating from the clouds, 10.4. This more critical influence causes the polar regions typically to have a concentration of ethane lakes, 10.5. Time-lapse images have shown clouds moving over hours to days. Dune formations show hints of locally shifting surface breezes. Reflecting seasonal variations, the polar lakes of methane and ethane are more conspicuous near the poles during winter, darkness, and less plentiful during summer sunlight. Titan's meteorological conditions thus consist of wind, precipitation, and seasonal fluctuations. It has long been known that Titan, apart from Earth, has the only nitrogen-rich atmosphere in the solar system. When Voyager 1 visited Titan in 1980 and revealed that its density paralleled that of other icy moons, and that its surface temperature was sufficiently low to liquefy hydrocarbons, researchers speculated that Titan's surface would be akin to that of Ganymede, a somewhat more significant icy moon characterized by a mostly flat, cratered, icy terrain that might contain lakes, seas, or perhaps a global ocean of ethane or methane. Public interest in Titan grew as radar first broke through her orange haze to expose the outlines of continental-size formations unique from those seen on other frozen satellites yet resembling Earth's features. Titan's surface composition differs from that of other icy satellites, including Earth. Unlike the silicates on Earth and the largely water ice composition of Ganymede, Titan's crust consists of ice and granular organic molecules. Titan's topography reflects Earth. The terrain comprises dunes at mid-latitudes and rocky, fractured landmasses surrounding low-lying basins filled with liquids at the poles. Figure 10.4-6. For significant liquid volumes that discharge into flatter, low-lying plains, The terrain has raised topography intersected by dendritic channels reminiscent of converging streams or sometimes broad conduits. 10.4. Particularly near the poles during winter, radar imaging of the surface has become ever more thorough in verifying the existence of lakes or seas of liquid hydrocarbons. Recent images of Titan's northern pole taken while it was oriented away from the sun show a body almost the same size as Lake Superior, located on the Canada-USA border, figure 10.5. Small and large basins abound at different latitudes, suggesting liquid bodies could sporadically flood low-lying areas. The thermal energy of the apparatus caused methane sublimation upon the Huygens lander's descent into the basin. Intermittent flooding's hydrocarbons may quickly evaporate, leaving saturated basins. Some polar lakes have low radar reflectivity, suggesting considerable depths that would help to explain their longevity, figure 10.4c. Channels across uplands or basins may have evolved from the erosion or failure of surface terrain, resulting from the discharge of subterranean liquid reservoirs. Titan's surface form may thus be influenced by atmospheric precipitation and subterranean liquid displacement. Dynamic forces have sculpted Titan's surface according to rifts, discontinuities, and other signs of geological activity. Titan shows volcanic features, mostly releasing a slurry of ammonia water from these processes. Impact craters are rare on Titan. The tight atmosphere causes only significant meteorites to reach the surface. Thus, we have found less than 12 impact craters. On the surface of Callisto, Jupiter's similarly sized moon, hundreds are present instead. Titan's history, therefore, has to be defined by notable weathering and resurfacing. Combining several kinds of data, including information on the planet's density and the composition and history of its atmosphere, helps one to build a thorough model of Titan's inside. We can thus generalize competing models despite their differences in the details, as shown in figure 10.7. In the first phases of Titan's evolution, a solid core of silicates and/or denser metals separated from water and other volatiles, including significant amounts of ammonia and methane. It came to define the planet's center. Radioactive decay and gravitational collapse continue to produce heat, driving ongoing geological activity. The heat flow from the core drives softer ice, including dissolved methane and ammonia, to the surface. The volatiles much lower the melting point of water. The heat emitted melts the ice below the surface, creating a worldwide stratum of a highly alkaline solution, including water, ammonia, and different organic components. Near the surface, the ammonia-water solution solidifies at low enough temperatures to preserve methane in a solid form. Water melts under sudden changes in thermal flow or other factors, producing a cryovolcanic eruption of methane gas and ammonia water. Saturn's largest moon, Titan, is a planetesimal, unmatched in the solar system. Although it is much smaller and farther from the Sun than Earth, its environment is primordial Earth, marked by mostly nitrogen and methane gases. Its dimensions and density are somewhat similar to those of Ganymede. Nevertheless, in terms of surface and atmospheric characteristics, it is quite different from Ganymede. Reconstructing Titan's history is difficult for such a far-off and mysterious object, since it helps one understand its uniqueness. The next book offers our simplified view of the studies and models suggested by authorities in the planetary science of Titan, 2, 4 to 6. In 1. Some 4.5 billion years ago, on the far-off outskirts of the solar system, the protoplanetary disk meant to create Saturn, and its moons started to aggregate. Whether from the distance from the Sun, the very low temperature at that range, or other factors, the reason for the abnormally high concentration of chemically reduced hydrogen-bearing molecules is yet unknown. Methane, CH4, and ammonia, NH3, were the most common occurrences. 2 here. Saturn gathered most of the material in the disk, condensing heavy elements into a metallic core sufficiently mass-bearing to hold hydrogen and helium. This produced a gas giant planet far more significant than Jupiter in our solar system. 13. Nearly 90% of the residual material dropped to the surface at a distance of 1.22 million kilometers, about 758,000 miles. It evolved into a composite of minerals and ice, strong enough to hold the volatile methane and ammonia, but not enough for the lighter hydrogen. This became Titan, the biggest satellite of any planet outside the Jovian system. Second in size, somewhat slightly, to Ganymede. 4, is it? Apart from the gas giants, the atmosphere made of methane and ammonia seems rather substantial. Perhaps the most voluminous and dense atmosphere of any planetary body during the primordial era of the solar system. Titan's position, more distant from Saturn's gravitational influence than Ganymede is from Jupiter, shielded it from the degree of meteorite impacts that stripped the atmospheres of the similarly sized Ganymede and Callisto. 7. Titan had enough water like other frigid outer satellites, but it was utterly frozen close to the surface at minus 180 degrees Celsius. Still, under the crust, the heat from the core most likely produces aqueous ammonia solutions. 4. Ionizing and UV radiation from space simultaneously interacted with atmospheric methane to generate more complex organic molecules. This created tholins, a haze covering the planet, 10.2. 7. Together with the denser tholins, the lower atmosphere was sufficiently cold to prevent methane and ethane from retaining their gaseous form, leading to precipitation. Initially, perhaps on an oceanic scale, ethane reservoirs flooded the surface and remain in ponds, lakes and seas close to the poles today. 8. The same radiation transforming methane into a more complex atmospheric mixture of organic compounds broke ammonia into its elemental nitrogen and hydrogen atoms. Titan's small size caused hydrogen to be lost to space, resulting in an atmosphere made mainly of molecular nitrogen, N2, with a higher 15N2 to 14N2 ratio. The 9th is Titan, which lost much of its atmosphere as it aged, but strangely kept methane. All calculations point to methane's disappearance long ago, unless it is being replaced. This is also relevant for the atmosphere of Earth, since biogenic sources mainly contribute to the relatively high methane levels. Although this phenomenon could also exist on Titan, most methane in Titan's atmosphere comes from its interior venting, backed by strong data of cryo-volcanic eruptions. 10 is Titan has been affected by significant meteorites, which need to be large to survive the dense atmosphere. Weathering and cryovolcanism have caused the craters created by these rare events to not suffer for very long. Thus, Titan's surface stays constantly young. The conditions for life on Titan are ideal in many ways. Titan has a thick protective atmosphere surrounding the satellite, subterranean and surface liquids, and many carbon-based biomolecule precursors. From the known life perspective, the circumstances of existence are appalling. For water-based life, the surface temperature is too low, the liquids are rather non-polar, and there seems limited possibility for a chemical cycle. Can life as we know it exist in a far-off part of the universe? Every press release on the latest Titan observations starts or ends with the presumption that scientists view it as a possible analogue for conditions on ancient Earth. Organic molecules are indeed relatively abundant. That sums up everything. Titan's composition, solar distance, orbital characteristics, dimensions, temperature, and nearby celestial bodies differ significantly from Earth's, suggesting that their histories have certainly changed from the first. Should Titan prove to be supportive of life, it is more likely that we will find the variety of life on other planets than have a thorough knowledge of the beginnings and development of life on Earth. Titan's environment is a rich storehouse of organic molecules. Upper atmosphere methane and nitrogen produce several hydrocarbons, nitrites, and polycyclic aromatic hydrocarbons, PAHs. Titan's cold atmosphere ionizes some smaller organic molecules, which increases reaction kinetics. Researchers have found negatively charged molecules on a scale similar to many amino acids. We need at least two essential components to prove that living entities exist on Titan. First, one has to be able to set limits similar to membranes, enclosing the metabolic systems of terrestrial life. We propose that the subterranean reservoirs on Titan are aqueous ammonia solvents. Lipophilic membranes can behave similarly in these solvents as in an aqueous solvent. Still, ethane and methane surface pools are expected to show more complex membrane chemistry. In ethane, the tholins falling as solid deposits are insoluble. They could link to form a sheath or film in hydrophobic liquids displaying structural stability. Silicon compounds, such as silane or polysilane, could be part of particular structural barriers, since silanes show stability under very low temperatures under reducing conditions. Given the fantastic range of glass, plastics, and other materials generated on Earth that can contain liquids incompatible with water, it makes sense to build semi-permeable boundaries stable in organic solvents. Such possibilities are still hypothetical. Nevertheless, we do not know the surface chemistry of Titan. The synthesis of instructive molecules, more significantly, large molecules with different structures, is the secondary need for chemical building blocks. Titan should simplify this process since carbon polymers are the best substrate for macromolecule synthesis with high information density. Figure 10.8 shows a basic approach for synthesizing a biopolymer using molecules found on Titan. Synthesized with hydrocyanic acid and other nitriles, this elongated polymer has a carbon-nitrogen backbone -N equals C-C-N equals C-C-. Every alternate carbon atom would have a different chemical group corresponding to the 4 different nitrogenous DNA bases, figure 2.7. The way the varied groups are set reflects information. If we suppose the existence of a template mechanism controlling the sequence of side group incorporation, it is clear how information gets duplicated. On Titan, a polymer of this kind could be present, but its existence is yet unknown. Chemical energy wouldn't be a problem in a world entirely made of materials akin to gasoline. Oxidation on Earth converts carbohydrates like glucose and sucrose and hydrocarbons like methane and octane into water. This mechanism uses oxygen to split the CC and CH bonds, storing the energy in different molecules. Titan's atmosphere consists of tiny amounts of free oxygen. On Titan, water is a significant source of oxygen, but it is completely limited inside solid ice and hence inaccessible for chemical reactions. Likewise, carbon dioxide freezes solid. The atmosphere contains higher carbon monoxide levels. Recent research suggests that the slow influx of oxygen ions from space and water from nearby moons like Enceladus may balance the carbon dioxide and carbon monoxide concentrations. On the other hand, some molecules might have used the energy from these reactions for medicinal purposes. Still, the oxygen available for this purpose is far less than required to keep life on Earth. On Titan, another kind of energy could be more logical. Titan's higher atmosphere's photochemical synthesis of larger organic molecules generates significant possible chemical energy. The great energy in acetylene, Hc equals Ch, makes it instead appealing. Its C-C triple bond gives this effect. The triple bond is broken during the reaction of acetylene with hydrogen to generate methane, releasing energy, 910. This offers a pretty interesting possibility for Titan, since it can occur in an organic solvent, such as methane and ethane. Whether enough reactive hydrogen can make this a realistic possibility still remains. We can confirm that Titan's surface contains liquids. As proposed, they mainly consist of liquid ethane, including dissolved methane, and different chemical compounds in solution. The very low temperature suggests that water cannot exist on the surface as a liquid. Underneath the surface of Metabolic, the temperature rises to a level where methane and ethane cannot coexist in a liquid form. Still, methane is probably kept as a clathrate, or caged molecule inside a water lattice under high pressure. Ammonia, which reduces the freezing point of water, is probably present in an aqueous solution at this raised temperature, and shows a pretty basic pH. Titan is quite chilly. A stable temperature of about minus 180 degrees Celsius, 290 degrees Fahrenheit below zero, at the surface suggests that water is solid. This temperature lets methane and ethane exist as liquids on the surface, somewhat above their melting points. Enough solar heat absorbed in the upper atmosphere raises the temperature enough for methane and ethane to evaporate. This lets them live as gases until they drop to the cooler areas close to the surface and condense as precipitation. Strong bolides would produce enough heat to transform water-ammonia combinations into liquids, producing transient surface pools. Under a frozen crust, an impact crater at least 15 kilometers in size could retain liquid ammonia water solutions for hundreds to thousands of years while fast freezing on the surface. Titans do not currently show any evidence of surface bodies of water. Temperatures underground rise toward Titan's core. The temperature at great depths exceeds that of aqueous ammonia solution's melting point. Two data lines support the possibility of large liquid reservoirs under the surface. Titan's rotational period is much different from the surface's spinning, suggesting the existence of a global subsurface layer of water separating the mantle from the satellite's core. Second, radar imaging reveals significant liquid reservoirs underground. We propose that gravity contraction and heat from radioactive decay induce cryovolcanic eruptions. This is proof of the Earth's higher interior temperature. Titan's low temperatures may prevent aquatic metabolism as we know it, but they could also moderate the activity of very reactive chemical species, including free radicals. Essential for a different kind of energy metabolism, these reactions would operate best in Titan's temperature and solvent environment, even if they are useless on Earth. Titan is the only central celestial body in the solar system with two distinct liquid environments. An aqueous solution, including ammonia and organic molecules, provides a potential habitat for aquatic life below the surface. However, with a more alkaline composition, this ecosystem could be worldwide and similar to the subsurface ocean in Europa. Seasonal fluctuations in availability and scarcity produce the oscillation of ethane-rich ponds, lakes, and seas, which include more significant, more complex organic compounds above the surface. Periodically, falling rain erodes the surface and refills the reservoirs with liquid methane and ethane, figure 10.10. Though Titan's mean precipitation is probably a few centimeters yearly, the organic rainfall on Titan is assertive, akin to southern United States torrential rains, probably displaying even more ferocity. The expected pattern of precipitation is one dictated by air movement. As such, monsoon seasons on Titan are a clear possibility and resemble. Still, the frequency of monsoons in any one location on Titan remains unknown. Where liquids flow or persist, they leave layers of tholins. Derived from lipids of non-polar environments, the geosphere resembles terrestrial desert habitats, which are often arid although rejuvenated by occasional rain. Precipitation revitalizes the basins by accumulating liquid, and the streams by flowing. But on Titan, the substance is ethane and methane instead of water. The two ecosystems probably cross momentarily because of irregular geological events like cryovolcanic eruptions, but they remain essentially separate. From an astrobiological perspective, Titan is fascinating since any life existing most likely started on the Moon. Titan's remoteness from any other celestial planet where life may have existed makes panspermia The spread of alien life? Unlikely. Furthermore, it is possible that life started in two different environments on Titan separately. At least two other situations have to be considered in the development of life since its arrival on Titan, independent of its source and habitat. During Titan's early years, when the satellite was presumably surrounded by a large, if not global, ocean, life's emergence and first evolution most certainly reflected the path followed under like circumstances on Europa. One crucial difference is the higher concentration of organic compounds, which might have accelerated the development of self-organizing systems into living entities faster than in any other place in the solar system. Titan and Europa differ, most notably in their much lower sunlight intensity. Sunlight on Titan is less than 2% of that on Earth. Though photosynthesis might take place at low light intensity, other energy sources are more competitive and would have been more plentiful. For the ancestral form of life in Titan's early aquatic environment, a primordial chemoheterotroph is thus the most likely choice. Still, heat and kinetic energy could have provided another bioenergetic source. Thermotrophs and kinetotrophs may thus have evolved quickly from this primordial species. As covered in section 10.3.1.2, methanogenesis via acetylene reduction is a fascinating theory implying that benthic and lithotrophic methanogens might have been among the first life forms on Titan. The primordial ocean carried easily accessible organic molecules. Titan's first organochemotroph would have been a microorganism suited to using this plentiful high-energy fuel source once biochemical pathways for processing were established. Originally on the ocean floor and then at the ice ceiling as the ocean froze, this progenitor could have produced many descendant forms, including microbial biofilms. Like jellyfish on Earth, flotation filter feeders and other mobile consumers may have evolved to provide nutrients for higher-order flotation and mobility. The kinetoscope's progenitors might have produced both benthic and sealing ciliates, and benthic reeds powered by water currents. Consumers like sealing scrapers could have evolved to target these producers. Equally likely, as other eaters, are microbial detrivores and more sophisticated fungal-like detrivores. The high dissolved ammonia concentration made the water alkaline, which requires adaptation among all living entities in this ecosystem. The first organochemotroph might have been specifically in charge of hydrocarbon management. Hydrocarbons would have been in higher concentrations in the sporadic bodies of water on or close to the surface. Thus, this adaptation would have been especially fitting. Significant meteorite impacts that produced ammonia water craters for prolonged periods, between hundreds and thousands of years, may have allowed an alkalophilic heterotroph able to tolerate hydrocarbons to flourish. The aqueous solution would return to an unknown state upon freezing, a hydrocarbon habitat where life on Titan began and evolved. Titan's surface had frozen entirely, enclosing any last liquid from the primordial ocean under a thick layer of granular ice and organic matter, when temperatures sufficiently dropped for ethane and methane to precipitate. Basins formed in uneven terrain where ethane gathered in pools big enough to generate seas, 10.5. On the same planetary body, two separate worlds now coexisted. An underground hydrosphere made of ammonia water, and a surface liposphere dotted with ponds, lakes, and seas of hydrocarbons, 10.9. Presumably, life began in the ancient, now subterranean hydrosphere kept in liquid form by Titan's internal heat, and the freezing point drop brought about by ammonia and other solutes. Thus, whether life in the liposphere above may have evolved from an aquatic progenitor, rather than independently developing in a unique hydrocarbon environment on the surface arises. On the one hand, living in ethane would call for such unique qualities that an independent origin seems likely. Titan's metamorphosis from a liquid water habitat to a frozen scene of ethane and methane lakes would not have happened instantly. Before falling to the surface, tholins gather in the atmosphere. capturing methane in the water as it turns to ice. The substrate finally changed to become a sludge high in petroleum, which put pressure on the organism and let it better adapt to hydrocarbons. All life forms, we hypothesize, in the liposphere descended from a single progenitor, an ancestral hydrophobe. Titan has many chemical molecules, suggesting several sources of the first biological systems. We assume, for simplicity, that they all sprang from the same ancestor. Figure 10.11 explores two different routes of possible ancestral hydrophobe origin. Chemoheterotrophs developing as self-organizing systems in liquid ethane, or methane, show a potential source of life, since hydrocarbon-based life starts independently from aquatic life. On the other hand, an ancestor who might have lived in hydrocarbons and aquatic surroundings could have adapted rather well to liquid ethane. This produced the ancestral hydrophobe necessary for life in the liposphere. Still, the last common ancestor and all following liquid hydrocarbon life displayed somewhat different characteristics from those detailed. These properties comprise 1. A structural limit that stays constant in a hydrophobic solvent. 2. An internal solvent that stays liquid at 380 degrees Kelvin temperatures, making liquid water impractical. And 3. The ability to sustain metabolism at temperatures much below those already investigated or rigorously modeled. These alien characteristics notwithstanding, they have become rather important on Earth. Studies have revealed that Fusarium alcanophyllum may proliferate and break down saturated hydrocarbons with limited oxygen and water supply. 12. This organism creates a strong barrier between the intracellular environment and hydrophobic surroundings by having rich fatty acids in its membranes and lacking more hydrophobic lipids. Another notable deviation from standard cellular architecture is the absence of internal membranes. Furthermore, researchers have found a notable presence of microbial life in a liquid asphalt lake in Trinidad, an analog site for studying life in hydrocarbons. 13. It is difficult to imagine a suitable solvent for life at -180 degrees Celsius. Nevertheless, two reasonable options exist as theoretical ones. Even lower than the freezing point of pure ammonia, the first substance combines ammonia and water that remains liquid on Titan's surface at -98 degrees Celsius. Cellular raised by metabolic activity could use it as a polar solvent. As we currently understand, polar solvent-based biochemistry would not be impossible in this case. The melting point of methane is -182 degrees Celsius, and the boiling point is -162 degrees Celsius. It is a non-polar substance. The liquid ethane-methane environment reflects this temperature range rather precisely. Though they would be alien to us, biochemical reactions in such a solvent could occur at roughly normal temperatures. The metabolic challenges are significant, starting with breaking down significantly reduced organic molecules in a less oxidizing environment. Researchers found a naturally occurring strain of Bacillus cereus in a Chinese oil field that breaks down long hydrocarbon N-hexadecane, 14. On the inner membrane of the bacterium, a unique collection of enzymes has evolved to break down the unusual carbon source. Many anaerobic bacteria can live in and break down petroleum sludge. One common approach for using microorganisms to treat hydrocarbons is choosing strains that, over many generations, progressively shift from metabolizing traditional carbon sources to hydrocarbon substrates. In geological terms, what fast achievements made by artificial selection should be available for natural selection to impact over rather long times. No Earth parallel somewhat captures Titan's actual conditions. Like other cases of extremophilic life on Earth, they show how natural selection might help unusual features arise in response to atypical selective pressures. Given millions of years to evolve in an increasingly colder and hydrophobic environment, there is no reason species quite unusual by Earth standards might not arise. Whatever the starting conditions, lithohydrophobes living in niches under the substratum would have evolved from ancestral hydrophobes, The heat of the Huygens lander may have released methane from the substrate, saturating Titan's surface with hydrocarbons. If such is the case, microbial hydrophobes living in the saturated substrate could be standard independent of their position under hydrocarbon pools. Should these organisms be methanogens and exist in significant numbers, their generated methane could help to replenish atmospheric methane constantly. Possibly related to the liposphere, ethane biofilms living on the substrates of ponds, lakes, and oceans reflect an early counterpart of it. In these hydrophobic biofilms, the organisms could be aggregated or a single creature spanning a significant area, like the behavior of slime molds that combine their cells to form multicellular entities under some conditions. These biofilms would have proliferated over the hydrocarbon pool substrate, protected from desiccation by the superjacent liquid. Still, the later ethane precipitation might have revived the cryptobiotic biofilms that survived pool evaporation. Biofilms could proliferate anywhere, so biofilm grazers developed to eat them. They most certainly lived in those conditions. Two further descendant forms that might have evolved are flotation hydrophobes and encrusted filter feeders. They would have enabled the rise of higher-order consumers, such as a megabubble floater able to feed on smaller liposphere inhabitants. Images of the channels on Titan's surface sent by the Huygens lander and Cassini satellite show them as if they were covered in a black material like tar on Earth. Many experts think this could be a layer of tholins expected on a theoretical basis to cover a sizable area of Titan's surface. We shall call it an ooze of a particular type. Whatever its composition, it could include species particular to that specific makeup. We speculate that some ooze residents fit this niche. Should biofilm grazers have developed to eat biofilms, they could have produced ooze burrowers that dig out the oozing and feed on their occupants. The two hypothesized biospheres on Titan would require two different ecosystems. Apart from Titan's subsurface hydrosphere, which is probably more alkaline, the underground hydrosphere is expected to be similar to Europa's. Like that body, the hydrosphere would be split into two main zones with microbial and stationary producers on the substrate, and above the underground ammonia water reservoirs. As the distance from the producers grows, floating forms could occupy the intervening volumes at a reduced density. Apart from Triton, Chapter 11, the liposphere would seem unlike any known entity on Earth, and could be unique within our solar system. This biosphere has two main components. One, on the substrate of liquid hydrocarbon pools, and the other, along the channels where a fluid amalgamation of ethane and methane flows downward as a viscous ooze of tholins resembling tar. We propose that the shallow trophic architecture of both main ecosystems on Titan indicates a limited extent of food chains. Our justification is based on the idea that 1. The extreme cold limits mobility, so complicating a predatory life. 2. The abundance of organic nutrients reduces the probability of consumer activity. Though a theoretical possibility, the presence of consumers in Figure 10.11 is somewhat conjectural. The main factor deciding any life on Titan is extreme cold. The abundance of organic molecules provides both structural elements and potential energy sources. Should a mechanism to capture this significant chemical energy develop during the early stages of evolution, Titan's biological traits would depend on the efficiency of metabolic enhancements. These would be shaped by Titan's unique chemistry, and limited by that chemistry's capacity at high temperatures. Titan has many organic compounds on its surface, atmosphere, lakes and seas of petrochemicals, and under its surface. Thus, self-organizing metabolic systems developed early in evolution to use plentiful chemical energy. Two elements that could lower hope for the fast stabilization of metabolism in this environment are 1. The lack of free chemicals to support intense oxidation reduction cycles, and 2. The inhibitory effect of low temperatures on reaction rates. The first problem could compromise our terracentric viewpoint. which usually depends on oxygen-containing compounds to oxidize organic molecules. Though little oxygen finds its way into Titan's atmosphere, it is in a relatively limited supply, and not enough globally for bioenergetics. Double and triple unsaturated carbon bonds abound and offer possible energy sources. Section 10.3.1.2 methane from acetylene. Still unknown, though, is whether enough reactive hydrogen exists. On Titan, nitrogen can replace oxygen, enabling oxidation reduction cycles. 15. Indeed, among many hydrocarbons, an infinite supply of carbon-bonded hydrogen exists, depending on using thermodynamically favorable processes to transform them into molecules like acetylene for energy release. One must realize that evolution is rather creative. There is no reason to doubt that a new, unknown metabolic pathway may have evolved under Titan's conditions to provide the energy required for any possible life forms. Likewise, cold is a relative term. Extremophiles evolving on Earth show how responses to the current environment lead to adaptations, while natural selection demands reactions occurring quickly at the required temperature to fulfill their necessary purposes. All chemical reactions occur at a slowed rate at lower temperatures. Metabolic rates will change soon enough for need. From our vantage point, Titan's metabolic rates are probably slow, but we should exercise caution since we know nothing about the type of those metabolic changes. Using lots of resources and energy in a cold environment, we predict simple reproduction and slow development. On Earth, heterogeneous and stable environments lower reproduction rates and slow growth. Evolution has usually optimized adaptations for success in stable environments, lowering death rates. Reducing their progeny count helps organisms preserve energy by allowing them to grow slowly towards usually larger terminal sizes. Evidence shows that Titan's weather varies regularly, and that habitat fragmentation is evident. Still, it is expected that the subaqueous or ooze-embedded liposphere and the subterranean hydrosphere would be stable for a long time. The general concept of reduced rates of growth and reproduction should govern Titan. To expect sexual reproduction would be unrealistic. Finding partners and sharing genetic material calls for energy and carries some risk. Hence, biologists usually claim that the advantages of gene recombination exceed these disadvantages. Many think the benefits come from a constantly changing genetic repertoire, which helps the organism adapt to new challenges and avoid diseases or parasites. If no new challenges develop for an extended period, and abundant nutrients enable chemoautotrophy to be a realistic way of life for all, reproductive simplicity is most likely. This could represent asexual reproduction or expansion-based growth. On the other hand, if parasitism is common in Titanian life, it could help sexual reproduction to evolve. We already mentioned the possibility of repeated monsoonal precipitation, producing seasonal cycles of rivers, streams, and lakes. Like species on Earth whose life cycles are closely entwined, with significant seasonal fluctuations in their habitat, hypothetical life on Titan may also be connected with seasonal fluctuations. For instance, species may lie dormant until the ethane-methane monsoon season, particularly in Titan's mid-latitudes desert sands, much as plants in the southwestern United States expect rare rainfall to bloom. Other species living in or near the ethane-methane lakes nearer the poles may similarly await the monsoon to drop organic nutrients from the atmosphere down the slopes. Reliable data on seasonal changes on Titan complicates even well-informed speculation. Still, if life on Titan has evolved to thrive in organic hydrocarbons, it would be odd if their life cycle were not in direct line with the seasonal precipitation and ascent in organic molecules. What is the meaning of movement if the search for partners is extraneous and organic nutrients are everywhere? This is likely why natural selection on Titan lacks a basis for fostering the evolution of motile life forms. Although they could be found at one or more consumer levels, they are probably few and slow, in line with the relatively flat ecosystem structure described in section 10.5 above. Titan's surroundings resemble a moss-covered forest floor, populated by a few animal-like entities. On Earth, sensory systems developed as navigational tools for locomotion, giving creatures spatial awareness, discriminating between friends and enemies, and enabling the necessary muscular actions for appropriate behavior. Should the creature be stationary, its need for sensory data is almost non-existent. Still, a chemical milieu high in nutrients would help olfaction to evolve. Touch sensitivity is essential since mutual recognition or antagonism drives the social interactions among microorganisms, particularly biofilms. Without illumination in Titan's surroundings, vision would be useless. Predator-prey interactions depend on sound detection, which is probably not required in settings low in predators. Primordial sensory processes like touch and olfaction started in the earliest microorganisms, devoid of specialized brain structures. Although the advanced senses of vision and hearing call for nerve cells, their absence does not clearly show the need for a neurological system. An emergent ability of neural systems, cognition implies that animals lacking such systems are unlikely to be thinking. Life is metaphorically represented on Titan as the pond covered in algae or the grassy expanse. Though it lacks intelligence, the biomass could be rather significant. Titan is an attractive prospect for anyone looking for unusual living forms on another celestial body. It combines alien properties, including organic compound liquids and very low temperatures, with known life-sustaining elements, including carbon-based chemistry. The appeal of letting our minds stray is excellent. An analysis by the National Academy of Sciences found that if life is an intrinsic property of chemical reactivity, it should exist on Titan. Thus, we have only suggested what is scientifically feasible, given our present knowledge. Still, that knowledge is rather limited, and the possible results are quite hypothetical. We are not sorry for reasonable conjecture. Nevertheless, this call to objectivity requires a corresponding caution remark. Titan's environment is very different from the known habitats for life on Earth. Our knowledge of the general limits of life is inadequate to determine whether it can exist under the unique circumstances existing on Titan. We suggest that life might exist under circumstances beyond human understanding. We might, however, be mistaken. If life depends on liquid water, it cannot exist close to Titan's surface or in that fascinating world. Titan has been a fascinating satellite in our solar system since its discovery over 350 years ago. Originally discovered, the sixth known moon of any planet was historically thought to be the largest and the furthest distant giant moon from its parent planet. Titan's nitrogen and organic-based atmosphere added to its appeal. Still, that environment remained mysterious until the Cassini orbiter and Huygens lander broke through its dense organic haze to reveal a surface with surprisingly terrestrial features. Dendritic channels running into basins intersect substantial elevations to show land subject to cycles of precipitation and erosion. Tectional-like formations and cryovolcanic eruptions point to ongoing geological activity. Rare and significant impact craters point to extreme erosional processes, rare impacts, or both. The discovery of major ethane reservoirs in Titan's poles supports theoretical hypotheses that the moon's cold temperature, -180 degrees Celsius, is sufficient for ethane and some methane to precipitate from the atmosphere and persist on the surface for extended periods of time. Titan's atmosphere comes from a somewhat bigger primordial envelope of ammonia gases. Photolytic degradation turned ammonia into nitrogen and sent hydrogen into space, annihilating methane. This produced a significant buildup of hydrocarbon molecules and ions, turning the atmosphere into a furnace of organic compounds. Some compounds produced tholins, which layered themselves upward to the surface. Mainly, the methane concentration stayed the same. This could indicate the continuous methane emission from a sizable subterranean reservoir, or the natural methanogen generation. Two distinct environments define the possibility of life on Titan. Based chiefly on water-based ammonia solutions, considerable evidence points to large subsurface reserves of liquids, maybe worldwide. This hydrosphere supports a complete aquatic ecology by matching the presumed biosphere within Europa's subsurface ocean. The tar-like tholin layers at the bottoms of channels and potential basins, including liquid hydrocarbons, and the liquid ethane pools on the surface, may each provide a unique habitat. This liposphere would have to sustain a unique biosphere of species, evolved to flourish in organic solvents at temperatures much below the possible liquid water. Theoretically, if life existed on Titan, its biomass may be substantial, but its trophic structure would be simplistic. Its many forms are predominantly sedentary, and its metabolism is unprecedented in our experience. The pursuit of life on Titan holds significant relevance as it would enhance our comprehension of life overall if discovered. However, scientific prudence necessitates acknowledging the possibility that it may be absent.